Hello, everyone. Oh, I think you can start. It was too loud, yeah? No? So it's my first time here at Delegates Belgium, and I'm really excited being here. So raise your hands if it's your first time too. Oh, a lot of people. So you won't get these jokes about the food quality being better, because I've heard it's getting better, but I cannot really relate because it's my first time here, and I really enjoyed the food. And I hope you'll enjoy my talk as well. So today we'll talk about static analysis for Kotlin. So please make sure it's the topic you wanted to listen to, because I'll shut the doors and then there will be no way back. So before we start, let me introduce myself. My name is Margarita, and I work as software engineer at Sonar. And I also speak at conferences, and I used to organize conferences in my native city, Kyiv. And I'm also a big fan of different programming languages, especially JVM ones like Java, Kotlin, Scala. And I honestly had a 3 years romance with TypeScript, but it's done. Now it's mostly JVM languages. And this is my Twitter or X handler. So you can follow me. Sometimes I tweet some stuff. And usually after this slide, I continue with my talk. But today I think there is one more important thing you should know about me. I'm Ukrainian, and I was born and raised in Kyiv, and only for 3 years I live in Switzerland. And you know probably that Ukraine is now struggling. We have some problems with our neighbors, and we need all the help that you can give to us. So if you haven't spent all the money on Delegates Belgium ticket, I'll encourage you to, if you feel like, to make a donation to our charity fund, Come Back Alive, because it really helps our Ukrainians to fight for our freedom. So that's the most important part of my talk is done. So let's get back and have some fun. So what we are going to do today. This talk will be, for my first time, very practical, very hands-on, so we'll do a lot of live coding, but we still need to have some theoretical knowledge, just a little tiny bit, so we'll have some static analysis intro, then we'll implement some tiny static analyzer by ourselves, and then we'll actually discover what we achieved and do some, learn some takeaways. And before we start, please raise your hand if this UI is familiar to you. Do you know what it is? Oh, a lot of people, but still a lot of people don't know it, so I encourage you to use it. This is SonarCube, so actually the product I'm working on. And this is how the report of one random Kotlin project looked in a previous LTS, SonarCube 8.9. I really encourage you to remember these numbers. 64 bugs, 39 security hotspots, 400 code smells, and 4 days of technical debt. It's some random project. And then SonarCube 9.9, it's 1.5 years after LTS. It's exactly the same project, so it's the same snapshot, the code base hadn't changed. But you have 3 times more bugs, you have 200 vulnerabilities while there were 0, you have 120 security hotspots, 2 times more code smells, and 1 month of technical debt. Nothing changed in the code base. The only thing that changed is the Sonar. So the only thing that actually changed is me and my team doing my job. You may think that my job is to make your code being worse, but that's not actually true. So my job is to find as many as possible issues in your code so you can fix them, and your code will be more readable, reliable, maintainable, and secure. So my job is actually to make your code better. I won't talk a lot about what actually happened because it's actually a different talk, but if you're interested, I encourage you to watch my talk from Kotlin Conf. This is more theoretical and less hands-on talk. And this is a YouTube recording of this talk. So let's get back to our ships and talk about static analysis. I'll try to explain people how static analysis works in simple words, and then I come up with some example. Usually, when we talk about static analysis, we are using your code. So you often write some code, and let's, for example, have some hello world class and some function there. And the static analysis is to take this code, transform it into some structure like tree. It's often called abstract syntax tree. And then we traverse this tree, find some patterns, and yeah, sometimes for people it's hard to get what is abstract syntax tree. So in this talk, we'll replace all the abstract syntax trees with AI-generated trees. So it's easier for you to spot. And then we'll take these trees and find some issues and generate the report. So static analysis is like this traverse from your source code to the issues through AST. But sometimes there are cases when just AST is not enough. So we need some semantic model. What I'm talking about, like we have one file where we have class hello world, and we have a different file with function v, which takes hello world, which has argument of a type of a hello world. And how do we know that this hello world is actually this class? And how do we know that this function is actually this function? In order to know these relations, in order to come from this node to an absolutely different node in another abstract syntax tree, we need some sort of a map of relations. And semantic model, in some ways, it's a map, it's a structure that contains all these relations between different trees and different nodes of these trees. And by having abstract syntax tree and by having semantic model together, we can try to build something nice. So let's stop talking and let's write some code. And because, of course, like disclaimer, it's impossible to write proper static analyzer in 30 minutes, I prepared some skeleton for you. I just wrote some dummy class analyzer that takes, in a constructor, takes some rules and has a function analyzer that takes list of files and class path. And here we are actually doing what I explained. We connect, in our case, to the Kotlin compiler. We generate abstract syntax trees and put it into source files variable, and we generate semantic model. And here we just traverse over these files and over the rules, visit them, and if needed, report some issues. So it all happens in the rules. And what are actually our rules are? Our rules for Kotlin, we are using Kotlin compiler API, are just visitors on Kotlin files. And these visitors, we also have some additional function add issue, so we not just visit, but if we find some pattern, we report an issue. So this is our API. Let's get back to our main class. Let's write some code. So our first dummy room would be just to learn. So let's just implement it here. So it would be anonymous class rule. Like, what do we want to inspect here? Let's inspect that if your function names start with underscore, we'll report an issue that this is a bad name. So we want to report like bad name rule. So if this is a visitor, we want to override some visit method. So I want to visit, sorry, not auto-completing, and I don't remember everything by heart. Yeah, I want to visit function, and you can see there is visit function type. Probably it's not what I want, and visit named function. Visit named function is exactly what I want, because we need to check function name. We know there's a function, it has a name, so perfect. And because we control this, we are sure that this context is always non-nullable because we pass it, so we can remove this question mark. So what do? We take the function, we take its name, and please notice that here name is nullable. So I am doing it like this. Why? Because we are visiting named function, and we imagine that we are in a case where everything compiles properly. And that's why we can check that it's non-nullable. So we extract it to a fun name. And then we write some if. If fun name, come on, fun name starts with underscore, we report an issue. Say context, add issue, bad name, and we need to pass an element on which you want to report an issue, so this is function. And yeah, we need some test files because we need to test it on something. Yeah, let's import on Java util arrays, for example. You can definitely see that this import is, sorry, it's not about imports. I'm a little bit nervous. So we have function f with a proper name, and then we have function with underscore. So we'll see that this function should not be reported, and this function should be. Let's check if it works. Yeah, we got some issue. So we have only one issue. It's on start line 5 and line 5. So seems like this one. So everything works properly. Exactly, we wanted to report here because it starts with underscore, and we didn't want to report here because it's okay name. So we learned it. We wrote something, and then you always have this colleague or this friend that comes to you like almost when you're done, when you want to release and when you want to push something to master, say like, you forgot something. Say that he tries our code, our rule on this example, and it doesn't work. So, okay, let's do it. Let's test it. Because what we usually need to do, yeah. He says that with anonymous function, it doesn't work. When I look in my code, I see like how it could not work because we are only visiting named functions. So anonymous function should not be there. Let's run it. And indeed, it fails with null pointer exception. If you go and check, it fails here with null pointer exception. Okay, now it's time to step back and ask ourselves why we put this non-null assertion here. Because we, like sane people, we thought that if we visit named function, it means that this is a function with a name. However, that's not true. Named function is the function that is declared with keyword fun. And it doesn't mean that an anonymous function is still KT named function. So we cannot easily put non-null assertion here. We have to also cover some cases of null. So the most correct example would be to do it like this. And we don't need this anymore. So exit. Yeah, now everything works properly because we don't get here if name is null. So one interesting finding, don't put non-null assertions if you're not sure. And even if you are sure, double check. Because we've been caught with Kotlin compiler multiple times assuming this. Okay, we implemented our first rule. Then let's implement something useful because this rule doesn't seem to be useful. And as I probably spoiled to you, we'll work on a rule which is unused import rule. Because for some reason, this is the most important rule for our users. Because they like it so much, report it so much, and so on. And yeah, I think this rule requires own class. So I already created a dummy class, so let's start. How do we want to write unused import rule? Let's firstly maybe collect some references. So how do we want to do? We will go through the file, we will collect all the references, and then we'll check if the imports that we have are used in these references. And if it does not, then it means that our import is unused. So we'll collect some references, and we will have to report some issues. So, okay, and of course, let's write some test. I've already spoke to you, yes? Java util array list or arrays. So we can definitely see that this import is unused. But let's try if our rule actually works. Yeah, so you'll see it works. It reports one issue on the line, on the third line. So we'll double check. Yeah, it's correct. So we are done with this rule. Please raise your hands if you think we are done with this rule. Yes, smart people. Yeah, of course. We again have our colleague or our friend, the most annoying friend, said that no, we are not done because your rule doesn't work with companion object. Okay, let's go to our example. And and we have file two. So you see here we have a class with some companion object, and here we have, come on, why it's duplicating? So, and here we have a class that is using the companion object. Definitely see that there are no unused imports here. But when we run, we see the issue on the line 4. So what do we usually do in this case? We have to debug. Yes? So let's debug. Let's put a breakpoint here and see what's actually going on. I don't know if the font is fine for you, because I cannot really control this debug font. But yeah, if you see this, you can see that here in references, all the fully qualified names have companion and companion my constant. And of course, in imports, we don't have companion. And that's why our algorithm fails. So we need somehow to handle companion object. Yeah, and so we'll have to remove this one. And we'll have a little bit change the way how we collect references. Yeah, so instead of having fully qualified names, now we will collect descriptors. And we will change the way how we report an issue. So what do we do here? We iterate over descriptors, we check fully qualified name, and if it's exactly the same, then we are fine. But if it's not exactly the same, we also checking that the name is companion, and we are checking that the parent is the imported fully qualified name. So let's check if this algorithm works. Yeah, no issues, so we fixed it. Okay, do you think we are done with this rule? Of course, no. So again, we have the same guy coming back to us and say, yeah, but like it works with companion object, but when I'm using named companion object, it doesn't. I'm like, okay, let's get back to our IDE. Let's check. And my class, now we have companion object named. Like maybe raise your hands if you ever use this feature. Like I have no idea why they need it, but yeah. Just to make a static analysis, people suffer. What? You can have only one companion object anyway, right? Yeah. So, yeah, for some reason, when it's named, it doesn't work. And when we debug, I'll probably a little bit save our time, we don't have any companion here, we have named. And here is the problem. We cannot know like what name this has, because it's in a different file and we cannot like take all different names here. So what should we do? So we should now step back, remove all this thing, and thankfully there is a way in Kotlin compiler API to check if something is companion object. So we don't need to check for exact companion string. We can just use some Kotlin compiler function, but the only problem is to find it. So as we found it, we can try, and yeah, it works. So we are done with companion objects, but we are not done with the rule. Once again, what do you think what could be next? Next time, our friend is coming that, okay, it works perfectly well with named companion objects, but when I decide to remove one file and not analyze it, you report issues. Like, okay. So here I have to show you some stuff. In order to be able to find semantic model and to analyze things, we need to have some context. And if we don't have other files or other compiled classes, we cannot resolve types. Here, when we run the analysis, we pass two files, file 1 and file 2. But if we, for some reason, forget to pass file 2, we will have an issue. Why we have an issue? Because while this class exists, our analyzer doesn't know about this class. And this class is unused because there couldn't be find any mappings between these two. So what can we do? The easiest way that we can do, we can find all these imports with problems and collect them. So we collect all unresolved imports and filter them out. Unfortunately, it means that if there is something really unused, we will not report an issue. But for some reason, users of static analysis prefer false negatives more than false positives. So what we do, we just replace it with unused, with this filter. And now when something is unresolved, it's not reported, fixed. Do you think we are done with this rule? Maybe raise your hands if you think we are done. Now, here your friend that is going to complain to you. And next point is delegates. So I think we are short on the time, so maybe I won't show you all these examples, so I'll just tell you that our algorithm doesn't work on delegates because delegates will need some special treatments. And yeah. And then once we fix it with delegates, have the issue with operator invoke. What's the problem here with operator invoke? The problem is that here you can override in any object, you can write function invoke, like operator invoke, and then you can actually call this object as if it's a function. And from static, like from abstract syntax tree, there is no difference whether it's a function call or it's an invoke operator. However, for the imports, it's a big difference. So we need somehow to find all the possible calls and check if they're invoke or not. And of course, it's very expensive operation, so we try to use lazy evaluations for this. But still, at the moment, we can do nothing with this because there is no difference between just calls or calls of invoke operator. Okay, we fixed delegates, we fixed operator invoke. Do you think it's the end? Like, please raise your hands if you feel it's the end of the story. Okay, let's try. No. I'm now curious what this guy has, because I thought we fixed everything. No, not really. So this guy is saying I'm trying to analyze this code, and it says me that function Kotlin streams to list is unused. However, you can definitely see that it's used. Okay, let me try this. So, so here is an example. Oh, interesting. We haven't actually started trying our code, but we see that IntelliJ reports that this is unused. So it shows me that this import is unused, and then it shows me that I cannot use list to list. And with an interesting message, IntelliJ tells me that I cannot use method to list because it's Java 16 higher, and I am on Java lower than 16. And if you run this code, it runs perfectly well. So this is the bug in IntelliJ, already reported. What's the point? The point is that in Kotlin, there is an extension function to list. In Java 16, there is a member function to list. And if we take the precedence, your own function, member function, takes the precedence over the extension functions. However, if you are on Java 11, for example, as we are, you can see that in JVM toolchain we are using JDK 11. It should be fine because you don't have this function to list. But for some reason, when we are running our analysis, we also report this as an issue. What the problem? Here, it was actually an interesting problem. It's the problem in configuration. You can see that here we hardcode the JDK release property as 21. So it means that while we analyze our code, compiler thinks that Java is of 21 version, and it has to list function, and that's why it messes up with imports. If, for example, we said that JDK release is 11, you see we changed nothing, just JDK release, there is no issue. Because in JDK 11, you don't have function to list in Java, but you have extension function, and everything works fine. So the proper fix for this would be to get this JDK release not hard-coded, but getting from the environment. For example, from your Gradle or Maven configuration, or maybe set by user in a property. But that was a pretty interesting bug. So yeah, we fixed it. And yeah, I won't take much of an intrigue here. Your friend won't come to you, but it doesn't mean that you don't have issues in your code anymore. We still have a lot of false positives, still not perfect, and for us, for writers of static analysis tools, it's a never-ending story of trying to balance between false positives and false negatives and actually reporting something useful. So every time people are coming, complaining, we are fixing the things, bugs, and try to catch these bugs before they reach the production. So let's now summarize what we achieved today. First of all, we learned how static analysis works. I hope you learned. So then you wrote a static analyzer in 30 minutes, which is a good achievement. Then we actually integrated with the Kotlin compiler. It was not easy for me to integrate for the first time, so it's a great achievement. We implemented 2 rules, unused import and bad name, and we fixed 6 false positives in our code. So, and there are a few takeaways that I want you to learn from my talk. First of all, Sonar supports Kotlin, just a subtle advertisement. That if you're having Kotlin in your project and you're not using our static analysis, you make me sad, because you can use it for free, and I try to do my best to make the best Kotlin. Me and my team try to do our best to have the best static analyzer for Kotlin. Then, static analysis for Kotlin is fun. Like you've seen, there are plenty of features, syntactic sugar, and you always have fun, and you'll never know how people use this or that feature. Static analysis for Kotlin is sometimes pain, but usually fun. So yeah, sometimes debugging, investigating these issues It's painful, but I still have some fun by learning stuff. And be active community member, because the issues that I showed you are actually based on our community feedback by real people reporting issues. Or you can think like be active community member as never underestimate the power of complaining. So here are the links that you can use. This is a link to my project, demo project, and this is the link to my YouTube talk from Kotlin Conf. Thanks a lot for your attention. I hope it was interesting for you. And if you have any questions, I think we don't have time, but we can definitely speak after my talk. And looking forward for your questions and your reactions.